we present SafeConstruct, a novel computer vision model that redefines construction safety violation recognition as a 3D multi-view engagement task. Today, safety monitoring is done manually by site managers. The goal of SafeConstruct is to automatically understand and assess safety compliance at industrial and construction sites using surveillance camera. However, directly applying off-the-shelf computer vision models in real-world construction environments is prone to multiple challenges. These include blurred footage, primary self-occlusion due to workers' poses, or secondary occlusion due to machinery or equipment, and distant or awkward camera angles which reduce model reliability. Although numerous models exist for human pose estimation and object detection, they often fail when deployed in construction environments due to domain-specific complexities. Traditionally, safety violation has been treated as a 2D object detection task. While effective to some extent, this approach suffers from a critical flaw, the lack of spatial depth. For example, a 2D model cannot distinguish whether a worker is standing in front of a ladder or behind it. Why SafeConstruct? Existing models are typically trained on crowdsourced or webmined dataset like Pictor v2, Pictor v3, and RoboFlow datasets, framing the problem as a 2D object detection task. These models lack 3D spatial understanding and scene-level worker-object context. Moreover, these datasets are small, with most images having unrealistic resolutions and perspectives, and lack construction-specific attributes such as depth, occlusion, lighting variance, and violation-centric annotations. In many of the images, the workers are in close proximity to the cameras. In reality, such a situation will never actually happen at a construction site. On the other hand, SafeConstruct leverages a multi-camera setup to reconstruct the 3D pose of workers and objects in real time, thus leveraging 3D spatial understanding and scene-level worker-object context. This significantly reduces occlusion-related failures. If a worker is occluded in one view, they are still visible in others. Let's walk through how SafeConstruct works. First, 3 to 4 cameras are placed around the construction zone, angled towards the scene center. These cameras capture multi-view images. The model processes these images using a 2D pose estimation backbone to extract joint positions in the standard COCO format. Simultaneously, a 2D object detection backbone identifies tools and site elements. This detector is trained on the synthetic dataset generated by SICSG, a novel synthetic indoor scene generator that includes variations in lighting, perspective, and background, enabling the model to learn physical common sense and spatial cues. Next, we apply bipartite matching to associate pose and object information across views and reconstruct the 3D scene. This allows the system to answer compliance and violation queries. For example, is the ladder being held by a second worker while the first worker climbs it? Since the system uses geometry-based pose matching and reasoning, it is highly generalizable to new sites without retraining. Further, the model's runtime is independent of the number of workers, making it scalable. Whether 1 worker or 10 are present, the frame rate remains stable. Additionally, it supports any number of cameras, with a minimum of 2 for 3D reconstruction. More cameras lead to higher violation recognition accuracy. Now let's look at some results. Here, we show both safe and unsafe scenarios with 2D reprojections of workers and objects. Safe examples include wearing a hard hat or properly climbing a ladder while being assisted. Violation cases include improper handling of large objects like windows, or multiple workers on a platform simultaneously. Quantitatively, SafeConstruct significantly outperforms 2D single-view formulations. With 4 camera views, it achieves an average plus 7.6% improvement in violation recognition accuracy. In one test, the system successfully recognized that only 1 worker was on the platform, even under indoor lighting conditions. In another, it identified that a ladder was not being held while a worker was climbing it, even under overexposed, high sunlight conditions. The model also supports entry-exit tracking and re-identification of workers. It also accurately detected when a worker was not wearing a hard hat in various lighting scenarios. We also explored some edge cases. In one, a hard hat was not detected. The system marked the event as a violation and continued to do so until the hat was worn again. Another example shows how adding more camera views improves prediction accuracy. Finally, let's view a live demo of Safe Construct. As a worker enters the site without a helmet, the system flags a violation. Once the helmet is worn, the warning disappears. When the worker lifts a window, the system recognizes the object and flags it as a violation since it requires 2 workers to carry. Later, when the worker climbs a platform and removes the helmet, the system again prompts for helmet use, showing the real-time, context-aware functionality of the model. By modeling safety violations as 3D spatial relationships, Safe Construct sets a new standard for vision-based real-time scalable and generalizable solution for safety monitoring in high-risk construction environments.